According to quantum field theory in curved space-time, and also according to Hawking radiation, it is possible to derive the lifetime of a black hole. So in this case, I will not focus on the derivation, because this is something that I have already done in a course on quantum field theory in curved space-time, but this is not the point of the video. The point of the video is to show you some numbers related to the lifetimes of black holes. So we start from a formula for the lifetime of a black hole. So L here stands for lifetime. This is just a subscript. And T is time. So it is the lifetime of a black hole, which can be written in the following form. It is a constant. Let's call it C, multiplied by the mass of the black hole, the initial mass, so m0 or m0 stands for the initial mass of the black hole. So after some time, the black hole will lose its mass, and at some point it will completely evaporate after the lifetime of the black hole has elapsed. And this is raised to the power 3. So m0 cubed is proportional to the lifetime of the black hole. So this is something that can be derived, and I will not get into the details of the derivation in this video. I will take this for granted. Also, let me tell you that this constant C, we can only take into account the order of magnitude in this lecture. I will not be interested in anything else. So I don't want to be precise. I don't want to give you precise numbers, but I want to give you orders of magnitudes. So in particular, this constant C can be written in a certain way, but I will just write the order of magnitude in standard units, so in the international unit system, and C is of the order of 10 to the minus 16, and then here there are standard units, so international units, SI units. So if you want to be more precise, you can rewrite TL also in another form. So it can be written as G squared, where G is related to the gravitational constant. It is squared, and then we divide by the Planck constant, the reduced Planck constant, and then we have the speed of light to the power 4. This factor here serves to adjust units in such a way that time can be proportional to ms cubed. So this is just the proportionality constant. Then here we have a dimensionless constant, b, divided by 3. So sometimes it is written like this, and then here we have m0 cubed. So if you want, this is just c. And this constant here, this proportionality constant, can be derived, as I said earlier. I will not get into the details, but if you plug in the orders of magnitudes here, where b is of the order of 10 to the 4, and it is dimensionless, so g is of the order of 10 to the minus 11 if you want, h is of the order of 10 to the minus 34, and c is of the order of 10 to the 8. So if you take all these into account, you get something like 10 to the minus 16 for C. And that's what we are really interested in here. We don't want to do anything precisely. As I said, we are only focused on orders of magnitude. Now, if we consider the mass of the Sun, which is of the order of, so this would be m0 in our case, m0 is of the order of 10 to the 30 kilograms for the Sun, and in this case it's as if we are considering a black hole with this mass. So this is the mass of the Sun, so it would be a black hole with the mass of the Sun, with the initial mass equal to the mass of the Sun. And if you do the calculation for the order of magnitude for TL, you get something like 10 to the 74 seconds. And just for comparison, you can think that the age of the universe is of the order of 10 to the 10 years, which is something like 10 to the 17 seconds. So this number exceeds, and it greatly exceeds, the age of the universe, just to give you the idea. And then what about, how about if we take the mass of the initial mass of the black hole to be much smaller than the mass of the sun? For example, we can take m0 of the order of a fraction of grams, for example, 10 to the minus 5 grams. So this is a very small black hole. So if we do the calculation in this case for TL, we get something of the order. So, I mean, the calculation is very simple because 10 to the minus 5 would be 10 to the minus 8 kilograms. And therefore, here we have, since the mass of so the initial mass of the black hole is cubed, we have 10 to the minus 8 cubed. So it is 10 to the minus 8 times 3, so 10 to the minus 24. Remember that we have the constant c, which is of the order of 10 to the minus 16. So we have to multiply this by another factor of 10 to the minus 16, and therefore this is equal to 10 to the minus 40 seconds. So these are seconds. And this is just a rough estimation, but it gives you the idea. And in particular, if we consider the so-called Planck time, T Planck, so Planck time is of the order of 10 to the minus 44 seconds. So this is not exactly equal to the Planck time, but we are getting closer and closer to the Planck time. And remember that in physics, the Planck time is that unit of time, so it's the smallest unit of time under which you cannot really make any meaning out of the concept of time. So if you want, in informal words, you can say that time does not exist below this threshold. So this is just some oversimplification, but it's what you can say. And some physicists like to write that even in books. But never mind. So this is just a small, sorry, a short video to show you some numbers related to possible lifetimes that black holes can have, and you can see that they span an enormous range depending on the initial mass of the black hole.